Swayam Prabha. Digital India. Educated India.
Welcome to the last session in this particular module. In the paper related to Organic Chemistry 2, we have been studying so far about the reactions of alkyl halide in module 2. So the last lecture is nothing but the nucleophilic substitutions summary of what we have studied so far. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH SwayamPrabha, MHRD, New Delhi. So what we will be covering in this particular summary session is basically the recap of all the informations we have studied related to the nucleophilic substitution reactions and the various factors that affect SN1 and SN2 reactions. Let us summarize what we have studied so far. The primary halides mainly undergo SN2 reaction as it involves backside attack. Increasing the size of the groups either on the alpha carbon or on the beta carbon will hinder the backside attack, that is the SN2 reaction. Due to this, the rate of this SN2 will be affected. In other words, increase in size of the alkyl group hinders the SN2 reaction. In the case of SN1, it is basically characterized by the formation of carbocations. So, bigger size of the alkyl group at the alpha or beta carbon will generally favor SN1 mechanism or SN1 reactions. And finally, depending on the type of the mechanism, if double bonds are present adjacent to carbon like allyl groups, then the rate of the reaction increases. And when we talk about the leaving groups, in both SN1 and SN2 reaction, the leaving group departs in the rate determining step. So, the leaving ability of the leaving group will play an important role in the rate of both SN1 and SN2 reactions. In other words, the better leaving groups like iodide will speed up the reactions. And among the halides, as we know, iodide is the best leaving group than fluoride. So it favors both the SN1 and SN2 reactions. In other words, the reactions involving iodide will be much faster compared to fluorides. And the charged leaving groups like oxonium ions, which come out as a neutral molecule, that is water, will also enhance both SN1 and SN2 reactions. With respect to nucleophiles, the stronger nucleophiles will favor SN2 reaction. Similarly, increase of the concentration of the nucleophile will increase the rate of the reactions of SN2. And SN1 reaction is independent of the nature or the concentration of the nucleophile, because in the rate determining step, the nucleophile is not involved. So, the nucleophile attacks the substrate only after the rate determining step. So, the nucleophile has no influence on the rate of the SN1 reaction. And with respect to solvents, usually polar solvents favor SN1 reactions as the charge separation in the rate determining step can be enhanced or stabilized. As far as SN2 reactions are concerned, the rate of the reaction can be influenced if the reaction is carried out in protic solvent than in aprotic solvent. Because in protic solvent what happens is the smaller nucleophiles, especially this is applicable only for smaller nucleophiles, they will be surrounded by the solvent molecules, making the substitution very difficult. At the same time, when the same reaction is carried out in aprotic solvent, the reaction will be faster. So this we had seen earlier with the comparison between fluoride minus and I minus. Iodine is a much bigger group, so it is less solvated compared to fluoride, which is highly solvated in a protic medium, alcohols or water medium. Let us quickly review some of the important aspects of the carbocation. So we will start with the reactivity. So what changes can happen to carbocation? The first one is the carbocation can combine with the leaving group, then it will get back to the starting material or the reactant. So this is basically the reversible reaction of the starting material getting converted to carbocation by the loss of leaving group. But if the reverse happens, we get back the starting material. Then the carbocation can be attacked by the nucleophile to give the substituted product. So this is also possible. This is the one we are actually looking for in the substitution nucleophilic reactions. Then the carbocation can lose a proton to give an alkene or olefin. This is also possible. Then the carbocation can also undergo 1,2 shift or rearrangement. These are all some of the reactions of the carbocation. And when we talk about stability of the carbocation can be stabilized by hyperconjugation. The carbocation can also be stabilized by inductive effect. The carbocation can be stabilized by the lone pair from the adjacent atom, especially the heteroatoms nitrogen, oxygen, which are having lone pair can stabilize the carbocation. And resonance or the pi bonds can also stabilize the carbocation if they are in the close proximity. And in the final summary, we can say comparison between SN1 and SN2. The SN1 reaction is initiated by the dissociation of the substrate into positive and negative ions. And again, the rate of the reaction is dependent on the substrate concentration only. So with this, we conclude the session on substitution nucleophilic aliphatic substitution reactions.